And of course, that is a link with statistics, where the inductive inference means generalizing from a limited sample to the whole population. That's also what we try to do in machine learning. It also links to a philosophy of science, where induction is also studied. And again, in philosophy of science, it means reasoning from concrete observations to some general theory. And so this aspect of machine learning links it to many other things like data mining, statistics, and general data analysis. And I think it's also useful to point out some, misconceptions that seem to float around about machine learning, because today there's plenty of people who equate AI to machine learning and who equate machine learning to deep learning, which is one specific type of machine learning that is extremely popular these days. So it's actually the one that has caused lots of breakthroughs. But there are other types of machine learning than deep learning, and there are other types of AI than machine learning. And so there's a bit of a history here about how many people see AI. So in the beginning, we used things like expert systems, which turned out not to work. Then we found machine learning, and then there was deep learning. But actually, the real situation is quite more complex than that. And Adnan Darwish has a very nice YouTube video, which if you want, you can watch, explaining the limitations of current deep learning, although I should say the limitations of deep learning 5 years ago, because by now some of those comments are no longer relevant. The field is, of course, moving at an enormous pace. But it's nevertheless to see what Darwish says about that. Essentially, a lot of the deep learning, he says, is about mimicking animal intelligence rather than human intelligence. Things like recognizing faces and so on, which a dog can also do, but it's very far still from human intelligence. Admittedly, things have been moving very fast even since then. But it is still important to see that there's still research going on all fronts in AI and machine learning, not just deep learning. And here's a very chaotic picture, but it's not nearly as chaotic as reality, I think, that shows how AI has what we sometimes call symbolic methods or logic-based methods, which do work well for some problems, and things like constraint solving actually is often this is very much on the logic side. And of course, you all know that these techniques are very successful, and this is still considered generally AI. But then for some cases, logic is too rigid, and you move to sub-symbolic methods, and that's where a lot of the deep learning today is. And so I'm not going to try to even explain this whole chaotic picture here, but basically there's lots of different parts of AI which all work well for different things. And also, if you look at machine learning itself, we try to define a little bit the machine learning landscape. So there's, of course, many different tasks that you can consider in machine learning. There's things like classification, which is a prediction task. Classify pictures of animals as being cats or dogs or whatever. There's regression, where you do the same, but you predict numbers. There's clustering, where you try to group things that are similar together, or reinforcement learning, which is, again, a totally different type of task. So you can actually look at machine learning and try to categorize methods according to the task they try to solve. But there's many other ways of looking at it. For instance, you could look at the techniques that are used in machine learning. And then you will see that techniques used include things like matrix factorization, convex optimization, transfer learning, so all kinds of different technical methods that are used inside the machine learning methods. And again, there's this research on all these different things, right? So you could look at all these methods as what kind of basic idea is underlying that method. And then you can look at what type of models we try to learn. And again, there's a huge variety there. So you all know, of course, the neural networks and the deep networks. There's things like decision trees and random forests, which are sets of decision trees. There's things like probabilistic graphical models and rule learning and lots of other things. So here we look at what is the shape of the model that the learner is returning. Does it have the shape of a neural network, a decision tree, an automaton? Again, lots of different types there. And then, of course, you can look at the applications, and that includes things like vision, which is a whole research area in itself, of course, natural language processing, speech, recommender systems, so places where machine learning is used. So part of the complexity of machine learning stems from the fact that there's no single way in which to best categorize techniques and so on. There's really many different dimensions along which you can try to describe machine learning methods. Okay, I'm going to try here, like I said, to start with some basic concepts. And so you could say, in the most typical form, machine learning means you look at an input, which is a data set, and you output some kind of model. And in a slightly more general form, you could say there is input knowledge. It doesn't have to be a data set. It could be any kind of theory. And you generate from that a more general form of knowledge, in line with what we call the idea of inductive inference, reasoning from the specific to the general. And then this categorization, of methods, already said, there's many ways of looking at that, but very often they're categorized according to the format of the input and output that they handle, and according to the goal of the learning process. As I showed before, there's many other dimensions along which you can categorize them. So let's have a look at a very typical task of machine learning. Let's say you have to recognize different types of fish on pictures. So there's here two types of fish, salmon or sea bass, and you have to, well, the computer is supposed to learn from a picture to classify them based on pictures, from examples, of course, of picture of fish and whether they were a salmon or a bass. And so one way to approach this could be you find certain features of the image as a whole, and here we have just two, lightness and width of the fish, so it relates a bit to the color as well. And it turns out that if you compute these features and you actually plot the pictures according to these two features, then it's clear that salmon are more like on the lower left, and bass are on the upper right. And that means that you could actually, so your solution to the learning problem could be to draw a line and say anything below and to the left of the line, I'm going to categorize as salmon, and the rest is going to be sea bass. And of course, there you can see some pink dots here to the left or some black dots to the right, so it's not a perfect separation. And then, of course, you can think, well, here's a better one. If I'm going to make the line turn a bit more, then I can actually perfectly match all the pink and the black dots, put them on the right side of the line. But I guess everybody sees that this is kind of random. If you had a different random data set, the line would have looked very different. So we're basically overfitting the training data. The specific shape of this line here is too complex. It tells us more about the training data than about some general aspect of these fish. So it's not going to generalize so well. And maybe the best solution is something in between, not a straight line, but one that could be curved, for instance. And this is something we often see. There's a trade-off between fitting the data perfectly and having something that generalizes as well. And this trade-off is one of the main problems in machine learning. You try to fit your data as well as possible, but you know that if you fit it too well, it's probably not going to generalize so well outside the training set. So how do you balance these two things? That's what a lot of research in machine learning is about. Okay, so that was a simple example of the basic principles of machine learning. You have some data, you can map that to some feature space, and then try to learn a model that makes predictions. It's a salmon or a sea bass, for instance. What we had here was an example of what I call this predictive learning. Predictive learning meaning the model that you learn is a function to which you can give an input, a thing that you want to classify, and then the function gives you an output, which is the class. So that's a typical classification task. But like I said, you have also things like regression, where you want to predict a numerical value. But there's many other types of predictive learning you can have. For instance, there's multi-label classification. Let's say you have a text. You want to say what the text is about, so you want to assign keywords to the text. But obviously, a text might be described well by more than one keyword. So you don't want to just assign one keyword, one label, but a set of keywords, a set of labels. And so that's what we call multi-label classification. And you can intuitively see it's quite a bit more difficult than assigning a single class, although ultimately not all that much more difficult. But still, it's a different problem. Or you have multivariate regression, where you predict a vector of numbers rather than a single number, multi-target prediction, ranking, where you're not really interested in the individual predictions, but you want to rank multiple cases so that the ranking you get is consistent with some target ranking. So this is all predictive learning, but it's different types of predictive learning. With descriptive learning, you get something very different. The idea is you have a data set and you want to describe certain patterns that you see in the data set. So for instance, you might have data about a bank and whether they gave loans to people or not, or mortgages or so. You might see a pattern, for instance, that the bank always refuses loans to people earning less than 1,200 euros per month. So that's an example of a pattern. Is that pattern something you could use for prediction? Only to a very limited extent, right? So if once you discover that pattern, you could say that anyone earning less than 1,200 euros should be refused a loan, and you would probably have a correct prediction. But if they earn more, this pattern doesn't tell you what to do, right? So it just kind of gives you some limits. It gives you some information about the data, but it's not by itself a predictive function. Have similar patterns here, like people who buy cheese at the supermarket are twice as likely to also buy wine. That by itself, that rule may not allow you to predict accurately who will buy wine and who won't, right? It's just, it makes you understand something about the data. So we call that descriptive learning. And what's important with descriptive learning is that the result has to be interpretable, of course, because that's the whole point. The description that you give must be understandable to humans. It's not like with predictive learning, where there is an objective way of checking the quality. Namely, you don't have to understand the prediction as long as it's correct, but for descriptive learning, the description by itself is what matters. So for predictive learning then, typically what we do is we learn a function that maps some input x to some output y, and that function may be descriptive or not. If you understand the function, if it's in a very interpretable format, then you could say it's also descriptive, but mostly function learning is an example of predictive learning. And the typical approach to do this in machine learning is you have a family of functions. So it's a parameterized function in a sense, have the shape of the function, but the parameters are unknown. That's what you have to learn. You try to find values for the parameters such that this function best fits the data. And of course, you all know things like linear regression. That's a very simple example of that. And when we say fit the data, we might mean something like you compare the predictions to the observed values, and you want to minimize the squared difference between these two. We call that quadratic loss. So this trying to find values for the parameters that minimize some loss, that's probably the most often used approach to machine learning these days. Of course, that only holds when you actually have parametric models, right? Where the model is indeed described entirely by parameters. So that was predictive learning, learning a function, but there's other things like distribution learning. You might have a set of data, and you want to learn a probability distribution that has a property that, well, these data are likely to, or are quite likely to have been sampled by that distribution. Try to find the best fitting distribution in a sense that this is a distribution that is most likely to be the real one given the data. That's one way of seeing this. And again, You can have this in a parametric or non-parametric manner. So parametric would mean, for instance, you try to fit a Gaussian based on this data, try to find the maximum likelihood values for the curve, for the Gaussian. Basically means try to find the Gaussian that makes this particular sample most likely. Non-parametric methods could, for instance, try to fit a curve through a histogram, and they would not have to fulfill like a simple formula like be a Gaussian or so. It's also interesting in this probabilistic setting to distinguish generative and discriminative models. So with the discriminative model, we basically assume that given an input x, you predict not a single value, but a probability distribution for the possible values of y. Okay, so this is still quite similar to function learning, but you do not give a single value as an output, but a distribution of values. But then this generative learning is quite different. You learn a joint probability distribution over the inputs and the outputs. What's the advantage of that? If you learn the joint probability distribution, not just for the output given the input, but also of the input itself, you can use that to generalize, to generate new instances by simply sampling from this population. At the same time, from the joint probability distribution, of course, if you want, you can actually derive a conditional probability distribution of y given x. Because once you have the joint distribution over x and y, all other distributions can be derived from that. So from that point of view, it's more general than discriminative, where you choose y and x in advance. But most specifically, a very important advantage of this is that you can actually generate new instances by randomly sampling from this joint distribution. And if you look at what things like DALL-E do, or even ChatGPT, when they generate text, is essentially sampling from a probability distribution. Ultimately, that's what they are doing. So these generative models are all somehow have some aspect of generative probabilistic models inside them. Now I was talking about prediction and description, and about the difference between predicting, so using a function, deterministic function for prediction, or probabilistic model. But these categorizations are a bit fuzzy. Like I said, I mean, a descriptive pattern may be in some cases useful for some predictions. It's just not a full predictive model by itself, typically. And also, even though if we want to predict just a single value, learning a function is enough, it's not forbidden to learn a probabilistic model and then predict, for instance, the value, if you get a distribution for y, predict the value that has the highest probability according to your distribution. That's still possible. I already talked about parametric versus non-parametric learning, and so parametric means you have a fixed format for your model and you just try to fill in the values for the parameters. Non-parametric, there you have no specific format for the functions, or there's typically something there, but very often the structure of the thing you're learning is also unknown. And very often that requires searching a discrete space, as opposed to parametric learning, where you typically search a continuous space. The values of the parameters are real numbers, so you have a continuous search space. When you think of decision trees, you can have a tree with 5 nodes or with 6 nodes, but not with 5.2 nodes, right? So there is something discrete about learning the structure. You search a discrete space. And one consequence of this discrete versus continuous is that the methods used for learning these models are also quite different in the two different types. There's a link also between these things I just said and explainable AI. So you probably know explainable AI is about AI that can explain its decisions to humans, which is in many cases very important. A bank that denies you a loan is by law obliged to explain to you why they denied you that loan, okay? So explainability is important. And there's actually two levels of explainability. One is you understand the model as a whole. Second is you can understand individual decisions being made. Again, the example of the bank. If the bank tells you you can't get a loan because in your particular situation, maybe you already have too many loans running and they believe you won't be able to take this additional one on top of that, it's enough for you to have an explanation why you don't get the loan. You do not have to necessarily understand the whole model that the bank is using for other people as well, okay? So very often a local explanation suffices, but there are these two differences between types of explanations. When we look at the model as a whole, then we talk about the black box model when the model as a whole cannot be understood by humans in any realistic manner. And of course, machine learning poses additional challenges for explainable AI because it often learns black box models, okay? So you might have an AI system that, I don't know, that drives your car or that, okay, let's say the system that drives a car, at some point maybe it stops without you seeing why it's stopping right now. You don't see a reason. You can't ask the car why it stops. Maybe it would be useful to be able to do that, to understand this behavior. But a lot of these AI systems have learned things inside, and these learned models are black box models, so in such cases it's hard to actually understand why it's acting like it does. So the type of machine learning method that you use inside an AI system will also have consequences for how well you can actually understand the behavior of the AI system. This is again relevant, well, for explainable AI, but generally for what we call responsible AI. What does responsible AI mean? You want systems that somehow, or that are employed in a responsible manner, giving due care to things like respecting the privacy of people, but also ensuring that the behavior of the model is safe. For instance, if you have a computer driving your car, you really insist that it is safe, okay? Safety means, in many cases, there's certain constraints, sometimes symbolic constraints, that it has to satisfy, okay? Like if you have a system that drives your car autonomously, for instance, you could say respecting the traffic law, that's hard constraints. If it says you can only drive 120 here, the system should actually abide by that rule. So you have understandable, interpretable constraints, hard constraints often, that should be satisfied by a system that inside has sometimes black box models. And so that's again a challenge here. How do you put that all together? How can you ensure that a black box model will satisfy certain constraints? And at the end of this presentation, I'm going to say something briefly about one approach that we used for that, and that actually makes use of constraint solving in a sense. Okay, I'm now a bit lost in where I am. Okay, so a bit more details about predictive learning. I already said what it is. Typically, you try to learn a function, this deterministic, sometimes probabilistic model. You want to have a function that tells you the label of a certain instance. And how can you actually get that function? You're going to learn the function by analogy to cases seen before. And that means that we assume that we have a data set where you have a number of instances that are labeled like cats and dogs, and then you have a new instance you want a function to be able to predict the label. And so you're going to learn that function by analyzing these data and somehow optimize parameters of the function so that it can actually assign the right label to the right instance. So this is the most basic form and sense of what we call supervised learning. And it's important here, of course, to distinguish the training set, which you use to train a system, and the prediction set where you're going to actually label instances that until now were unlabeled. And if you look at that particular setting, you could say it's supervised learning, you can actually still distinguish two types. And again, this is useful to make this distinction because it's often not mentioned, but different machine learning methods will actually behave in a quite different manner in a sense. So we can distinguish transduction and induction. What does transduction mean? In transduction, you get some labeled cases, some unlabeled ones, and the output of the learning is a set of, is actually the labels. So the predictions for these cases, that's the thing that you learn. And that is a setting that is often seen, for instance, in graphs. You have a number of nodes that are labeled, other nodes are not labeled, fill in the labels of the unlabeled nodes. That's typically a transductive setting. Now in induction, that's different in the sense that what you learn from the data is not immediately predictions. You learn a model that maps X to Y, and then you can use that model to make predictions. And the difference between the two is that this is generalizing more. You could also use the same function for yet new cases that you didn't see while you were training. In the transduction setting, you assume that everything for which you have to make a prediction is seen during training. You just don't have the label, which you need to predict, but you already know for which instances you're going to have to predict the label. So this setting is, in that sense, a bit easier. The transductive setting is a bit easier than the inductive setting. And again, for things like graphs, very often we have a transductive setting, but you could also have inductive settings in that context. I already talked about the difference between interpretable and black box models. I'm not going to, that's kind of redundant here. I've also briefly already mentioned the problem with overfitting and underfitting. So generally, like I said, there's a trade-off. And so if you have this set of points which roughly form a parabola, then underfitting would mean that you use a too simple model format, and it's not going to fit your points really well. Overfitting would mean that you use a too expressive family of models, and it fits your training data very well, but it's likely not going to generalize well. And so both underfitting and overfitting can happen and are harmful. So very often the challenge is then to find a hypothesis space or a family of models that is just expressive enough to be able to fit your data quite well, but not expressive enough to overfit the data. How do we do that in practice? Very often this is done by having a kind of, overfitting avoidance is done by changing the loss function into a cost function that also has a regularization term, which kind of punishes you for if you tend to make the function too complex. Now, I talked about supervised learning, but there's plenty of other settings as well, unsupervised, semi-supervised, and many things related to that. So supervised learning means I learn the model from labeled cases, right? Unsupervised is I learn it from unlabeled cases. And semi-supervised, some of the cases are labeled, others are not. And maybe it's a bit of a surprise that semi-supervised learning could actually do something useful. So how is it possible that, let's say I have 4 labeled examples here. If I asked you to imagine a line separating the positives from negatives, there's many ways in which you could do that, right? Now let's say you would, in a semi-supervised learning setting, if I would ask you to predict the value of that, the point that near the question mark there, some of you with their imaginary line might have it to the left of their separator, to the right, so you might have a plus or a minus. Now in semi-supervised learning, if you have lots of unlabeled cases, additionally to the few labeled ones, then if you see this kind of distribution of the data with a kind of river of emptiness in between, If I now show you this question mark, probably all of you will assume this is a negative case, right? Whereas in the original picture, that was not so obvious. And if the distribution of unlabeled cases would instead be like this, then we'd probably all assume that the question mark is a positive case. So knowing something about the distribution of the data, even if you don't have the labels of all these things, can actually help you a lot in finding a better model. And then unsupervised learning is, if you have something like this, this is typical clustering task. If you see that your input data are not uniformly spread, but you see kind of clusters of the data, the question is, can you identify those clusters? Those clusters are probably, I mean, they typically have some meaning. You could call these classes, except that you don't know the name of the class. But apart from that, if you identify the clusters, if you then see a new case, you would probably be able to assign it to if it's near one of these clusters, you would assume it's the same class, in a sense, as the other cases in that cluster. So this is the typical unsupervised learning, the prototypical unsupervised learning clustering, essentially. There's many other types or variants of semi-supervised learning, like PU learning is a quite interesting one. It's semi-supervised because you know some labels but not all. But in addition, only the positive cases can possibly be labeled. The negatives are never labeled. So you learn from some positive labels and all the rest is unlabeled. Why is this important? Well, if you think of, for instance, learning language, you have a picture here and the sentence, Mike is kicking the ball. And since it talks about the ball, you assume there is a ball somewhere in the picture, okay? But not everything in the picture is mentioned in a sentence. I mean, there's a tree there that's not mentioned. That doesn't mean there is no tree, okay? So basically, the fact that the ball is mentioned means that this must be a positive picture for having a ball inside. So you get, in a sense, a positive label there. But there's also a tree inside, but that's just, you don't get a positive label for the tree because it doesn't occur in a sentence. So in this setting, for many other settings, it's actually quite realistic that only positive cases can be labeled and negatives are typically not labeled at all. Other cases of semi-supervised, or what is sometimes called weakly supervised labels, are things like to show you a picture and I say it's either Ferrari or Lamborghini, so I don't know which of these two it is, but I tell you it's one of these two. So you have limited information about the label. The label must be in a certain set, but you don't know which one it is. This is a kind of opposite thing. There's only one label. There's a Lamborghini in this picture, but there's 3 cars, and I don't know which one is a Lamborghini. So this is multi-instance learning. So again, these are all examples of having some information about the label, and you could express this as a constraint that you have on what labels you have, but you don't have full information about the label. And so ultimately, when you look at all these different settings, there's lots of different ways in which you can have supervision. So if you look at predictive learning, supervised, unsupervised, or weakly supervised, and then you have all these special cases of those as well. This is relevant because it is useful to know that in many practical cases, even if not all the instances you have are labeled, it can still be useful to have those instances, and if you use the right learning approach, you can actually, it will benefit from getting these unlabeled cases or maybe partially labeled cases. Right, so until now I was mostly looking at a setting where you have a pair, an X, an input, and a label, Y, could be numerical or a set or a single class. That's one type of machine learning that we have a lot, but it's certainly not the only possible type of machine learning. And so let's have a look now at a quite different setting, which is called reinforcement learning. And reinforcement learning, you could say it's a kind of, it's a bit like partially supervised, but it's not, the differences are not just in the level of supervision. So you have an agent, like a robot or something, that can be in a number of states and it can take actions, and these actions change its state. And some of these actions may also lead to a reward being given, and you want to maximize your rewards. The agent wants to maximize its rewards in the long run. And then the question is, how should it behave? Can it learn to take, under certain circumstances, the right actions in such a way that it's, in the long run, the sum of rewards will be maximized? So formally, what we have is a state space, states that the agent can be in, a transition function, which given a state and an action gives you a new state that you move to, and a reward function, given a state and an action, gives you some number which expresses your reward, and there is a so-called discount factor, which implies that rewards farther in the future are less interesting for you than rewards that come earlier. If it's the same reward but you get it earlier, it's actually more valuable for you. So given these things, you want to find a policy, a way of acting, a way to make decisions about what action to take in what state, a policy that maximizes this thing, and what you see there is simply the sum of all the rewards you're going to have in the future for taking certain actions. But this gamma to the power I says that the farther away in the future it is, the less the reward is valuable right now. So it is kind of exponential decay on the value of the rewards in a sense. And what's important is that this transition function, reward function, are not known to the agent. If they were known, you would get something that's more similar to like a planning problem, but they are typically not known. So in a sense, the learner has to learn these things together with the policy. What's also very different from the previous case is that here, there is no fixed training set that you learn from. The agent will generate its own training data through exploration. So it might do a number of actions, starting from an initial state, make a number of actions, and just see what happens and what rewards it gets and so on. It did this a number of times, and after a while, it would be possible to learn this delta and R by doing all these things and observing what happens. But even if you learn delta and R, you're not there yet, because you want to learn this optimal policy, this policy pi, that maximizes your future rewards. Okay? So what we get typically in reinforcement learning is that this delta and R are not explicitly learned, but that you somehow still try to learn this policy. So it basically means that after a while, the agent has learned how to behave optimally, even though it couldn't, in many cases, still couldn't tell you exactly which rewards will be got or what the effect of this delta function is. It just knows that in this particular situation, I should be doing this. That's my best action. So in order to make it a bit more concrete, let's have a look at one of the most basic reinforcement learning algorithms called Q-learning. In this Q-learning, you're going to try to update a function called Q, a function of state and action. And this function in the learning process will ultimately converge to something that expresses the accumulated reward that you will get from first taking action A in state S, and after that, always taking the optimal policy. So the first action is defined in the Q function by this A, this parameter, but afterwards we assume you always follow the optimal policy. Now, if you could learn a Q function that converges to this, then in the end, this Q function will define your optimal policy pi star, because once you have an accurate Q function, in any state, it should choose the action that with the maximal Q value. Okay, and I mean that's going to give you a slightly higher reward in total cumulative reward than if you choose any other action. When you look at the formula there, and so by definition that will be optimal. So learning this Q function will give you an optimal policy. How is a Q function learned? You actually have a kind of iterative updating procedure where the Q function for a certain state and action is computed as immediate reward plus gamma, this is count factor, times, and then the maximal Q function of the next state, so the maximum value for over any action that the Q function will have in the next state. This is probably a bit abstract. It's maybe a bit hard to see how that will converge to an optimal policy, so I have a small illustration here. So let's say you have a robot that can walk around in this maze here, and there's a pot of gold, and basically nothing ever rewards the robot except when it finds the gold. In that case, it gets a reward of 1. And what you see up there at the top of the slide is this Q update rule that I talked about. This count factor here is assumed to be 0.9. So if we apply Q learning here, what's going to happen is that we just assume in the beginning that the robot makes random steps. So maybe I should still explain the tables. There's 16 possible states, the positions of the robot, and for each state, 4 possible actions going up, down, left, or right. And you see in the tables there the current Q value for each action in each state. And it's initialized as zeros everywhere. And then you let the robot just walk around, and we store the rewards that it gets for a certain move. And of course, in the beginning, it's basically moving around, and it's just getting rewards of 0, until at some point it's going to find the pot of gold. And now it goes straight for the gold, but that's kind of accidental, right? It's basically moving randomly, but this would take too long if I made it follow a different route. Anyway, at some point it finds the pot of gold, and that gives a reward of 1, and we assume that at this point actually it ends, so this is one episode of the training process. We're going to reset it afterwards. But before doing that, let's have a look at what happens to our Q values. So because the last move actually had an immediate reward of 1, the Q value for that action in that state would be 1 plus 0.9 times the maximal Q value in the state where it terminated, which is of course all zeros, so you get a Q value of 1. Now, because that one has a Q value of 1, the move before that led to this state did not give an immediate reward, but it led us to a state for which the maximal Q value now is 1, which means in that state, you know which action to perform in order to get a nice reward. So moving to that state where you know what to do next is by itself also a good idea. And so we're going to get this if you move all the way to where we started, you gradually update the Q values for all these moves. And what you see now is that the system has learned from here, for instance, that the best action to take in that state, when you look at the Q values of 4 possible actions, the best action is going to the left. It's also the only action it has tried until now, right? So you repeat this many times, and gradually these tables are going to fill up, and it converges to a Q function that has the property that whenever in an action, in a state, if you take the action with the highest Q value, then you'll be following the optimal policy. So that's Q learning. It's kind of basic example of how reinforcement learning in general can be addressed. There's lots of things to be said about that. So here I was assuming a table that has for each state and each action an entry that tells you how good that action is in that state. In practice, you may have way too many states, way too many actions to do that. So you might want to replace that table by a kind of model, a model of the Q function. Okay, so what you then do is you let the robot try out some things. You gather all these Q values that you get. You treat them as a training set that you then use to learn a model for the Q function in general. And the first time you do this, it's going to be a very poor approximation. But once you have this model, you can keep adding new data and improving the model, and ultimately you hope to have a model that gives you a good approximation of the Q function. And that's called model-based reinforcement learning. I was assuming a deterministic setting here. If you are here and you move left and you end up there, that's deterministic. But very often Q learning is set in a probabilistic setting, And then Markov decision processes are basically the way in which these things are analyzed, but the basic ideas are very similar to what I just showed. Also, in this QL learning algorithm, I'm assuming random exploration. I didn't say exactly how you should explore. I just assumed that the agent is doing some things, collects QSA values, and then tries to become better at reaching its goal. But I didn't say how to explore. You can do that randomly, but you can also do it in a more clever way, for instance, by gradually increasing the exploration in certain parts of the subspace that are more promising, so that you get faster convergence in those areas where where you want it, because those are the most interesting ones. Okay, so I talked about supervised and supervised and so on learning. I talked about reinforcement learning. There's a few other settings that are quite interesting, especially today, if you look at the methods that are used today. And one of these settings is what I call encoding data. And so the task here is you want to, given some input, you want to have a tool to learn two models, F and G. The first model should actually compute for this input some output, which is typically lower dimensional than the input. And then the second model should actually, from that output, reconstruct the inputs. So the models are, in a sense, each other's inverse. I have an x, I compute f of x, and if I compute g of f of x, I should have the same x again, ideally. So I'm really trying to learn the identity function. Now, you might wonder, how stupid is that? Why would you want to learn the identity function? It's like the easiest possible function. You already know it's the identity function. Why do you want to learn it? Well, the reason is we move from high to lower dimensionality. That means that ultimately you learn how to compress a high dimensional space into a lower dimensional space. Because if you don't do this, if you don't do this without loss of information, then this G will never be able to reconstruct the original X, okay? So by forcing a system to learn these two inverse functions, but forcing this middle layer here to be lower dimensional, you actually get dimensionality reduction. And sometimes this X, this input space, might not even be a vector space. You can think of graphs or so. And then we often call that an embedding. You move from whatever structure the space has to some vector space in such a way that the original can still be reproduced from that. This is useful for dimensionality reduction, for compression of data, and many other things, generally for understanding the structure of the input space. So you could think of a very high dimensional input space where the data actually lie on a manifold, let's say a kind of sheet in 3 dimensions with a form that you don't know, but anything on a sheet could be described in 2 dimensions. You could actually have a 2-dimensional coordinate system on the sheet. So that's an example of how you could learn to compress data onto this 2-dimensional structure, for instance, in such a way that you can reconstruct the original one. Sometimes the intrinsic dimensionality of data is lower than the dimensionality of the space in which they live. So F is here called typically an encoder, and then G a decoder, and this encoding and decoding is very often used these days in a lot of modern machine learning methods. Now, I was talking about a kind of deterministic kind of encoder-decoder. I have a point. It's mapped to a point in a lower dimensional latent space, and then you can reconstruct the original point. But there's also a probabilistic version of that, and what you have there is that we still have these functions f and g that operate on an individual element, but the goal here is to, if you have a certain distribution in your input space, the goal is not so much to reconstruct individual points given a certain input, but to map the distribution to a distribution in a latent space in such a way that if you map that back to the original space, you get the same distribution again. It's the same principle, but focusing on the distributions rather than on the individual instances. Now, F and G still operate on individual instances, right? But we no longer have the task, if I give an X here, that the output has to be exactly the same X. But it should have the same, the output should have the same distribution. Why is that useful? Once you have here in the latent space a relatively simple format for a distribution, even though the original distribution in the input space could be super complex, if you have this one, then you can start sampling in this space in a very simple manner, and then transforming these samples with your G, and you will get an output that has this original distribution again. So you can generate samples from some super complex distribution, okay? And that is how many generative models work. So if you think of a picture, a photo, it's a super high dimensional thing. All these, each individual pixel is a dimension. It's hard to say exactly what this distribution looks like. If it's pictures I mean, if you take a random point in this input space according to a uniform distribution, you will see just noise. But if you have human faces, then that's not just a uniform distribution over this input space. All these human faces are some kind of lower dimensional manifold. And once you have been able to identify that distribution and represent it in a latent space, by sampling in the latent space, you generate new faces essentially, not just random noise, but pictures that look like faces. And so that's how you can generate pictures, basically. Pictures that look good, that make sense to us, because you can sample in this intermediate space. When you think of things like variational autoencoders, for instance, that is basically this type of model. I mean, it's a kind of encoding mechanism, but looking at the distributions, not just trying to reconstruct individual cases. Okay, I should probably speed up a little bit. So I already said the format of the input data is important, and especially until like a few decades ago, statisticians and also machine learning looked at a standard setting where each instance is described by a number of variables and numerical value for that variable, or maybe a categorical variable. We call that the standard setting. But many things like pictures, graphs, and so on are not so easily represented in this standard setting. And so you need, if you would use standard statistical analysis or machine learning methods, like decision trees or so, or linear regression, they're not going to work very well if you do not have the standard setting. So the standard setting is kind of tabular thing that is most commonly used also in statistics, for instance. But examples of other types of input data include things like sequences. Let's say I have data where I'm telling you this first string, A, B, A, B, A, B, A, B is a plus, and the second string has a negative label. And you have to somehow find a rule telling me when something gets a positive or negative label. That kind of things, processing strings, the input data is very different than what you typically get in this tabular. It's not tabular data, okay? There's lots of other things. You might try to predict a label for each individual element in the sequence or for the sequence as a whole. Instead of letters here, symbols in the string, you could have numbers, and then you have time series and so on. So it's all sequences, all this type of data. And a sequence by itself is very different from the tabular format that we have. For instance, the length of the sequences could also be different. But apart from sequences, you can also think of tree-structured data. For instance, HTML documents internally have a tree structure, and if you want to assign labels to certain parts of the document, this can be useful in some cases. So the input that you have to train on here is tree structured. Again, so each individual element of the input is a tree. It's not the standard format. Graphs are even more complex than trees. Of course, I went from sequences to trees to graphs, and graphs are very often used these days. Again, you have many different types of tasks, like predicting labels of edges or predicting whether there is an edge between two nodes. And then there's what I call raw data, which is basically things like all the audio signals or pictures where basically there is nothing, no real well, there is some kind of structure on some kind of deeper level, but on on the highest, on the level of the pixel matrix, you just have lots of numbers, okay? And this is, of course, a type of data that deep learning excels at. So the strength of deep learning is that from such a picture, it can actually define features on higher levels that can then be used to actually actually classify the things it sees. So we have this Tableau data, then sequences, trees, graphs, raw data, and maybe the most general type of data, or the most structured one, is where we just have knowledge. For instance, let's say you have a molecule. You could actually describe the molecule in a kind of logic-based form by saying there's certain atoms and there are certain bonds between these atoms. Then you have a description of the molecule, but you can also put in some general chemical background knowledge. You could say, for instance, that certain types of atoms tend to accept hydrogens. So that's the definition of this HAC, hydrogen acceptors. There are things that we call zinc sites or hydrogen donors. So this is chemical background knowledge. You put all this knowledge in. So it's not just a tabular format we have here. It's not even just a graph. It's a graph with chemical background knowledge. And from that, you have to learn a model. In this case, it was about molecules that act as a drug against some disease. You want to learn which molecules will work well for this particular drug you want. So many different types of input formats, and they all require learning methods that are adapted to this particular type of input. Data may not always be in a format that your learner can handle immediately, and then we talk about data wrangling, bring it into the right format so that learners can actually process it. Now, it's not just about changing the format, this data wrangling. When you think of a picture, it's maybe just, it is basically a vector of numbers. So you could say, it's the right format. I have variables, namely pixel 1, pixel 2, pixel 3, and so on. But still, these variables are not very meaningful. So you need some kind of higher level meaningful features on top of that. And then we're in the area of so-called feature selection and feature construction, constructing features from the original data that are easier to work with if you want to make a decision. And so, of course, this feature construction is what's happening implicitly in deep learning methods. And that explains why they work so well. So generally, if you want to decide what learning method to use, it depends very much on at least the type of input you have. So this tabular attribute value format is in a sense the most basic one, the one for which that's best understood, for which most theory exists about how to learn from that. But other learners will be able to handle, of course, other types of data. Different learners also have different inductive bias. That's something I haven't talked about yet, but even if you have the same format of data, let's say clustering, for instance, which is unsupervised, some clustering methods tend to find round clusters, others will tend to find more like serpentine-like clusters. So the algorithm you use for clustering will have an effect on what type of data is likely to work well. So I had many different tasks. I talked about the type of inputs you might have, and then let's have a look at the type of outputs you might be having. So we output a model. What format is this model in? When you look at high level at machine learning approaches, there's a number of people who wrote books about them, not just these three that you see here, and they all have different ways of how to categorize methods according to what kind of output they give. And the output, of course, is related to the kind of reasoning they make. So I'm not going to explain these things in detail, just telling you that there are different views on what are the underlying, what is the best way to categorize different methods in terms of what kind of information they give you. And someone like Chris Bishop, for instance, takes basically a Bayesian learning approach to everyone, but others will actually try to to partition the space into multiple types of methods. So a very simple type of method is, of course, parameterized functions, where you have a function, let's say y equals ax plus b or something, could be another formula, and you just try to fill in the values for the parameters that fit the data best. But a totally different type of model you might want to learn is, for instance, a conjunctive concept, which is, and that's more like in the setting of symbolic methods. You try to find a definition for a certain class. X belongs to class C if it fulfills a conjunction of conditions. For instance, a bank might have that they will accept applications for a mortgage if your salary is at least 3 times what you will have to be paying back each month, and you don't have any more other mortgages already. So this is a specific concept that is learned, a condition under which, in this case, the bank would give you back the loan. And this is very interpretable, right? So maybe it's a bit confusing because it looks maybe a bit like the 3 times monthly payback may look a bit like ax plus b, but there we just learned the parameters, but here you would actually learn the conditions and the variables that have to be put, where the variables have to be put. A bit related to that are rule sets, so you could imagine trying to learn the definition of a leap year from examples of which years are leap years and which are not. And then you might have some kind of if, then else rule, multiple nested rules actually that define the concept of leap year. Another type of model that we often encounter, still on the kind of interpretable level, is decision trees, which look like this. A decision tree basically checks for the value of a certain variable, and depending on the outcome of that check, you move a different path down the tree until you reach a leaf, which gives you the answer to your question. Is today a good day to play tennis? You might first look at the outlook, and if it's sunny and the humidity is normal, for instance, that would give you, that would mean it's a good day to play tennis. So this is also the type of thing we can learn. Instance-based learning is a different type of method again, and here we don't really learn a model in any kind of symbolic or sub-symbolic manner. We're just going to store the data, and the data itself is the model. So when we have to make a prediction, for instance, we have an instance that's here, we would look at what are its neighbors, what are the points stored in the data most similar to it, and if they're all red, then we assume this one will be red as well. That's the basic idea behind nearest neighbor methods. Again, I mean, I'm now explaining basic ideas which are very simple, but you have all kinds of variants, of course, that can get increasingly complex. Probabilistic graphical models can also be learned, and you can still distinguish cases where you know the structure of the model and only have to learn the parameters, or you have to learn the structure as well. So what's a Bayesian network, for instance? That's one example of probabilistic graphical model. You have it's a representation of a joint distribution, where we say, for instance, that the probability of C, taking certain values, will depend on what the values for A and B are. So we have lots of conditional probability tables here, and the product of all these conditional probabilities together gives you a joint probability over all the variables. And the graph you see there is basically defining the form of this factorization that you get. So if you have a certain graph, then it implies that there exists a certain factorization that will give you the joint distribution, and then you can learn the parameters of each factor in the factorization rather than the parameters of the joint distribution, which is actually a lot easier because you're going to have much fewer parameters to learn. So this is basically learning probabilistic models. Neural networks, I guess all of you know these things. You have some inputs, you have one or more outputs. You're going to have a number, very often they are layered, you have a number of variables in the middle. And we train, so each of these nodes is actually dependent on its inputs, and you train the weights of all these connections that define that dependency, and somehow, in some way, you hope to find a network that represents the link between inputs and outputs. As such, networks are typically considered black box models. You have possibly thousands, millions, or even billions of these numbers inside, and somehow this network, while training, converges to something that works well, but it's very hard to actually see, look inside and see what it's actually doing. What we had here is kind of the basic format, just a number of layers stacked on top of each other. When you look at the neural networks often used today, the successful ones, they have a much more advanced internal structure that is, in a sense, hardwired to be good at certain things. When you think of convolutional networks, or SDMs, for instance, or transformer models, all of those are networks that have a certain particular format that makes them work well for certain tasks. And so as an illustration of this, let's have a look at how convolutional neural networks look. Basically, have an input, which could be a tensor. So it's if you imagine a picture, you have a height and a width, and also 3 layers, which could, for instance, be the RG and B values of each pixel. And then you have this convolutional layer, and then a pooling layer, and multiple convolutional pooling layers intermittently, and ultimately some fully connected layers in the end. But what this convolutional layer actually does is, given a certain kernel, a kind of pattern that you know is relevant, the convolutional layer, what it's going to do is it scans the picture for that pattern and makes a map. So you go over the picture and you kind of try to show where in the picture you saw something that resembles the kernel. And you do this multiple times, basically just scan the whole picture, and what you get after the scanning is a map that shows you where you find things that were similar to the kernel you were looking for. A single convolutional layer would do that not just for one kernel, local pattern, but for multiple, and then you get multiple of these maps. And then, okay, the pooling is not very important here, it's kind of reducing resolution a bit, but then in the next layer, these maps are going to be the new picture, so to say, although in this case it's very abstract, that you're going to again scan to look for certain patterns. And now you combine the information about the different patterns that you found earlier, so you learn higher level features here. But so the fact that they scan this picture, that is something that is just hardwired in the convolutional layer. What it learns, what this network learns, is the patterns to look for. That's what's learned by fixing the parameters. But this idea of scanning and making a map of where you found certain patterns, that's just hardwired in a network. Another example is in natural language processing. Let's say, for instance, automated translation. If you have a certain sentence, you could encode an LSTM. It's a certain type of network that goes over a sequence and has certain memory cells, so it can remember what it saw earlier and at the right time recall that memory. And what was done in this approach from 2014 is you go over a sentence and you basically, so these H's here are kind of internal state of the network. You go over the sentence and you end up in a certain state, and that state is supposed to encode the meaning of the whole sentence. So we call that the encoder LSTM. And once you have that state, you can use a decoder that decodes the state into a sentence, possibly in another language. So this is an example of where you see this encoder-decoder structure, where the encoder and the decoder have by themselves certain structures specifically designed to do certain things. In this case, to go over sequences and remember certain aspects of the sequence. The more modern approaches, like the transformers, work still differently. I'm not going to explain the details. In fact, these models are quite complicated already. If you read the original paper, it's not really, at least I did not find it possible to see exactly what happens there. They do use attention, and I thought I had something about attention written somewhere. I must have dreamed that somehow. But the idea of attention basically is that each word in a sentence gets enriched by adding information about it to it about neighboring words. And the attention mechanism basically tells you what to look for, what kind of words are relevant to actually add to this particular word in order to have a more richer meaning for it, and then you can actually translate that. BERT is yet an example, but I think I should probably speed up a little bit. It's an example, again, of such a transformer architecture. There's one more thing I want to say about search methods. So you probably know that models are typically learned using a kind of gradient descent approach. You have some loss function, and you move in some space. So to the right here is a so-called parameter space. For each of these lines that are a model you have, it's actually characterized by a certain combination of parameter values. You look in this space, parameter space, to reduce this loss, doing something like gradient descent, and that means if you look back at the original data space, that your line is kind of moving in such a way that ultimately you find something that fits the data quite well. Now this gradient descent kind of thing is quite well known, but there's other methods that will return, for instance, not a single solution, but a set of solutions. And a quite old concept there is that of a version space. It's set in a kind of symbolic learning context where you do concept learning, you try to find a definition for a certain concept, and the version space is basically going to look at the set of all possible concepts, the hypothesis space, and as you look at the data, it's going to try to eliminate from that hypothesis space everything that is inconsistent with the data, so you end up with a set of all possible correct hypotheses. We call that candidate elimination. And I don't really have time to go over this in detail. Let me just quickly show, like, the hypothesis space is organized into a lattice where the 4 question marks say this is like everything is positive, everything belongs to the concept, and this one says nothing belongs to the concept, this bottom symbol. And then as you see instances, like you see a robot that's misbehaving, that's a positive example, and it has certain properties, then any of the concepts here that correctly explain that this one should be misbehaving will be in the version space, the rest are out. And if you look at this lattice, what you go, so in yellow here you see the sub-lattice that still contains all possibilities. As you go through this, what happens is that with each positive case, you actually, the most specific hypothesis that covers all the positives is going to be generalized, right? You had one positive, have another positive, and then the most specific hypothesis that covers both in the lattice would be found by just moving up to the lowest point where the lowest common ancestor. If you have negative examples, then basically the top of this thing will go down, and often you can actually have multiple points for the upper border. And so you basically keep points here that are on the border, the most general and the most specific hypothesis, and anything between them is automatically also known to be valid. So this is an example of where you start with a hypothesis space, you kind of reduce the set of all things that might still be your solution set. And so what's interesting here is that you don't just find a single outcome, but you find a set of all possible outcomes, all possible solutions. And this type of approach is actually used in some learning approaches, and you can think, for instance, of association rules, which you might have heard of. You look for rules for things like, in a supermarket, people who buy bread and butter often also buy cheese. That's an association rule. And the methods for finding these association rules really typically try to find all association rules that meet certain criteria, not just a single one. So these are methods that return sets. And a similar thing is if you have, let's say, a logic-based database, you want to find constraints like fathers, whenever someone is a father of someone else, then this first person is male in the database. So there's a number of constraints you could find in a database. Again, we're looking for a set of such constraints. So machine learning can not only be used to find a single solution to something, like a best fit or something, but is also used for learning sets of solutions. And specifically in the context of constraints, for instance, that can be, of course, useful. Think of the nurse rostering example that I gave in the beginning. You're not specifically looking for one constraint, but all constraints that seem to hold in the data, right? Now, I promised to say something about our recent work. I have very little time left, I'm afraid. So I already pointed out how important it is to be able to trust your machine-learned model. Like in a car, it should not do anything stupid. You have certain safety constraints. And the problem with learning a neural network or other black box models is how do you prove that it's going to behave like you want, that it's not going to violate certain constraints. That's not just for neural networks, it's generally a problem. And so it would be nice if we could learn methods, learn models of which we are certain they will not violate constraints. There's actually multiple ways. I mean, of course, whenever you could have constraints, and whenever a prediction violates a constraint, fix it. That's a kind of post hoc, changing the outcome. But you could also try to use models for which that have been verified, for which it has been proven that it will never violate the constraints. You can do that sometimes using so-called model verification methods. And a third approach, which is in a sense even more interesting, is if you can have a learner of which you can prove it cannot possibly return a model that violates the constraints. So it certifies that your constraint that your model has to fulfill these constraints. Even if it's a black box model, there's a guarantee it cannot violate the constraints you want. Such things would, of course, be very interesting to have. Especially the third one, it's also very challenging to do that. And so one thing that we tried recently, and that's making a nice link now with the constraints programming here, is we managed to get some interesting results there by formulating the learning problem as a, well, it's often formulated as an optimization problem, but here we formulated it as a max SMT and array problem. What does that mean? We have a number of hard constraints that our model has to fulfill, and the training set is encoded using a set of soft constraints. Soft constraints saying basically, for instance, for this particular x, you have to predict a y that is not too far away from the y we observed. And in the context of regression, you can do it like this. You could say that you have a constraint that the difference between prediction and observation should be less than epsilon, but you do this for many different values of epsilon. Let's say ordered from low to high. And of course, the more of these constraints you violate, the further away you are from fitting the data well. So the quality of fit is translated to how many of these constraints you actually satisfy. And so we have a set of hard constraints and a set of soft constraints, and then we just run satisfiability modular theories with NRA, which means that you can do nonlinear real arithmetic. So it reasons about the parameters of a neural network, for instance, and using that reasoning, it proves that all the constraints will be satisfied. Well, that's what the max SMT does, right? I mean, it will find solutions that fulfill the constraints because that's what the thing does. So interestingly, we could translate this learning problem to a max SMT problem. You might think at first that's going to be way too hard, it's not going to work, and indeed it doesn't work just like that. We had to do a number of things on top of how we learn and so on. Basically what we do is we have an approximate method that still is guaranteed to fulfill all the hard constraints, but fulfilling as many of the soft constraints as possible. That's where we have something more like a heuristic. We try to fulfill many of them, but not necessarily all of them. That's not worse than what most machine learning methods do anyway. But you do end up with something that is guaranteed to fulfill the hard constraints. And so first version of that we had was only for linear models, but we managed to make it work also for neural networks with ReLU activation functions inside. So this is, I think, a nice example of the fact that machine learning can not only help constraint solving, but constraint solving can also help machine learning. And I think there's actually a lot of interesting things still that can be done there. That's the end of my talk. Like I said, I mean, I'll be around for today, possibly not the rest of the week, but if you want to talk to me, if you have questions about this or so, there's not much time to ask them now, I think. But I'll also be joining lunch, so feel free to ask them whenever you see me. Thanks for listening.